Okay, so hello everyone. Good morning. Um, I think we are going to continue the chapters. So basically, uh, we are going to start the how to solve the homogeneous linear system with our eigenvalues, which we are going to use the eigenvalues uh, by taking the differential equations, taking into matrix, with this with the um, solution that we can offer is that we have k e with the power of the eigenvalues e, and k is the eigenvectors, and the exponent why we need the exponent there, because that is the one way that we can solve a differential equation. Because if we remember in the engineering mathematics 1 or in calculus, when we have the exponent, we derive many times, it will always arrive at the same equation. So that's how we get that. And from the differentials, we can also rewrite that the idea for the eigenvalue is it makes the matrix A, the coefficient in the matrix, minus the lambda, and we multiply that with the eigenvector. This will be 0, and this would be possible if this part is 0, or if we need to satisfy this with the determinant for the A minus lambda identity is equal to 0. Basically, this is what we have from previous eigenvalues topics. We call this the characteristic equation. So we need to find lambda through this characteristic equation, that we are going to put the lambda inside our equation. And of course, from the eigenvalue, from the lambda, we also get the eigenvectors. So we get the eigenvalue, we check every eigenvalue we find, we get the eigenvector, and then we are going to put it into the solution. But now, for today's course, aside from the normal regular method that we may encounter, if you remember the homogeneous system in the engineering mathematics 1, there are few cases that we might have to discuss, and also our solution is not only one solution, but we need to make sure that we get every solution that are unique. Remember, solutions that are unique are it would require a linear independency. That's the first one, and the second one, we need to have the set of solutions, or we call the fundamental set of solutions. So that's the total solutions that we need to have for all cases. So we are going to explore that part in today's course, and hopefully we can finish that subtopic. So let me go through. The first case is we have the distinct eigenvalues. So let's say we have some lambdas, we have some eigenvalues that they are real eigenvalues, and they are different. They are different with each other. They are distinct. We call the distinct. And then we have the counterpart, the eigenvectors. Okay. So the general solutions depends on how many eigenvalues we might find. We are going to have each one of them in different set of solutions. So we call this the fundamental set of solutions for the homogeneous system. So we have the eigenvalue 1, eigenvalue 2, 3, and so on and so forth. And we have this as our solution. Of course, the first case is we need to find the eigenvalues and eigenvectors throughout the system. Okay? And let's explore some example here. Then we have the differentials for x, dx dt and dy dt. So we can, I think we can try to explore that part. Okay, now suppose that, as usual, we are going to write this in terms of the, so first is perhaps the x prime, and the second is the y prime. Okay? And let's write this in terms of matrix. So x prime is become 2 and 3, and this will be xy. Or let me just write this. Suppose that you get what is that? And y prime is 2, 1. And then we can write the system in one matrices. So we can define A as 2, 3, 2, 1. Okay. And then we can take the determinant and find the A minus lambda. So 2 minus lambda. Okay, we start by taking a simple 2 by 2 matrices. So finding the determinant, we get quadratic equations. Okay. So this will be 2 negative 3 lambda plus lambda squared minus 6. And we need to make sure that this will be equal to 0, right? So I will write lambda squared minus 3 lambda minus 4. And we can factorize. And we get 2 lambdas as we expect from the 2 by 2 matrix. So first lambda is, let's say, negative 1. The second lambda is 4. And then after we get the lambda, we need to find the k, the eigenvectors. And after we get the eigenvectors, then we are going to plug into the final solution, the fundamental solution for the homogeneous system. Okay, now we check each lambda. I think I will write this here. And this will be going over there. This will be going over here. Okay, I think that will be better. And then we check each one of the eigenvalue. So check for eigenvalue 1 equal negative 1. So we take 3 k1 plus 3 k2 equals 0. And then 2 k1, 1 minus 1, so plus 2. K2 is 0. And we could see that this is going to be k1 equal negative k2. So we could have k1 is 1 negative 1. Of course, we can have another combination that are possible. It's still okay. but let's say that is, and then for lambda 2 equal 4, this will be negative 2 k1 3 k2, and then this will be 2 k1. 1 negative 4 is 5, right? 5. Oh no, 1 minus 4, 3, negative 3 equals 0. So we have this one becomes 3k2. So k1 is 3 over 2 k2. You can have a fractions in your eigenvector, but I'm suggesting we write the whole numbers. So I will prefer the k2 as 3 and 2. So we have completed all the k1, k2 with each eigenvalues. Okay, so the solution we can write first, we write each solutions. The first one is the eigenvalue 1, so this will be 1, negative 1, and then e, then negative t, and then x2 will be 3, 2, e, and then the k is, or the lambda is 4, so this will be 4t. And of course, e with power of 4t and e with power of negative t, they are linear independence. So this is, we can still approve for these solutions. We can write the whole solution as c1 x1 plus c2 x2. So c1, 1, negative 1, so this will be the general solution. So general solution. Okay, so of course, if we are only having this as our solution, then we still have the constant, right? So it can be any constant as long as we fit within the equations. And to get the exact solutions, like sometimes the question may be asking the final solutions, then we need the boundary. We need the initial condition or the boundary value to get the C1 and C2. But here, in this case, it means that if we try to draw, we try to draw all the possible derivatives for all constant that is applicable, then we are going to have many lines that I think if you remember in engineering math 1, we have the slope field, which usually we get slope field from, so we try to cut a part of derivative, like a gradient for each line, and then we are going to see that for all possible, so if we change the constant, we change the slope field, so it's kind of like this. So we have like this one. we have this. Okay. So you can see that it's going to different constant. It makes different lines. And if we could see, for example, if we take the constant as 1 and 3, we get this, the first one. And then we have the other one, the other value as well. So we are going to have like a trajectory. Okay. So we can interpret these parametric equations as a trajectory, and we call this as a phase plane. Okay. Okay. So this is phase plane, this is trajectory. So trajectory. This is trajectory in phase plane, which means the xy. The first two, graph A and B, this is for x and t, y and t, the axis. And then if we combine the x, t and y, t, we get the xy, we call this a phase plane. So we combine these two equations into one. So this could be understood as dy dx. If you remember the parametric equations, we can have parametric xt and yt, and then we can eliminate the t to make it into y and x, or Cartesians, not normal Cartesians. And you will see that it has some red line that will be our basis. So let me write here. We can eliminate the parameter. So the two red lines is actually for half line defined in our parametric, defined as parametric. In first, second, third, and fourth quadrant by x2, negative x1, negative x2, x1. So the one line is going to be this one here. It's going to be y equal 2 over 3x, which is it's going to be parallel with the eigenvectors, because this is parallel with K2. K2 is 3, 2. Okay. And then this one, the other one, is going to be y equal negative x. This is parallel with K1. K1 is 1, 1. Oh, 1, negative 1. And you can also see the eigenvectors. You can confirm by looking at the directions. Okay, you can look the directions, both for, I think for the K2, since the eigenvectors are positive in x and y, which means they are going to move away, and you will see that when we have opposite directions in the vectors, 1, negative 1 for K1, you will see the arrow is going to attract and then it's moved to the origin. So that means, I think, if you remember the phase portrait in engineering math 1, we have the repeller, attractor, something that's like looks like this. Okay, let me write here. Looks like that, right? And then another one is the like that, or move away. We call this the stability, right? The stability of the phase portrait. Well, it works similarly. So we call this repeller. So repeller. A repeller is when the lambda 1 is positive, lambda 2 positive, and then we call it attractor. Lambda 1 is negative, lambda 2 is negative. Okay, so to make sure that we are still on the same definitions, let me write the solutions in terms of only the equations, okay, without the matrix. I hope you can differentiate the matrix and the other variables. I write matrices quite big like that. Okay, so if I write only the normal equation, I will write like this, okay, small like that. So this is only for the x. So I will just count the x of variable. So this is plus 3 C2E 4T, and y is negative C1E plus 2 C2E 4T. Okay, I think we are going to analyze more later on. And I think it's better to give you some more graphs that can be analyzed visually rather than this one. I think I will prepare some picture so that we can easily see the visualizations. I think, I'm not sure, I haven't tried taking the eigenvectors or the phase portrait system in MATLAB, but for parametric, I think it's easy to see. But I will try. If not, then I will just use GeoGebra and looking for someone who has built the code for the phase portrait, and we can change through our equations, okay? And we can see how it looks like more clear. And later, when we have the exercise, I think if you want just to find the eigenvalue and eigenvectors alone, using some tools from, I think, either using Python or MATLAB. Well, I prefer directly using MATLAB because it will give you direct results. If you're using Python, you need to define all the functions and you need to import library and so on if you prefer doing coding like that. But if you check MATLAB, it's actually quite easy to use. You can input just the number. Okay? You don't need to write the script, the code. What you need to do is just put the variables, put the numbers, and then just write egg and then the matrix, and then it will calculate immediately. And similarly with the eigenvectors, you can also compute the eigenvectors immediately. Maybe after we get all clear, I will show you how. Okay, maybe just in a quick glance, maybe next week. Yeah, next week. As long as you are, I think, student, you can use MATLAB for free for academic usage, so you can optimize that time. Otherwise, it will be very difficult to access the MATLAB. Okay, I have another example with a 3 by 3 matrix. So this is 2 by 2. I think 2 by 2 still okay. I mean, the computations, finding the eigenvalue and the eigenvectors is not that complicated. as long as you get the characteristic equation, you solve that characteristic equation, you get the eigenvalues, then I believe that is like the first steps in the procedure. it's done. Okay. Okay, let me continue for the other example. Okay, other example. Now we have three differentials. So we have a variable x, y, and z. And as usual, I will write a variable for matrix, and usually I will write as capital X. Okay. So we can write as a capital X to get the idea that this will be defined as all the -4, 1, z, 1, 5, yz, 1, sorry. This is 0, 1, -3. And this will be x, y, z. Let me make it x smaller. So this is our matrix A, the coefficients, and we are going to take the matrix A to find the determinants, completing the eigenvalues solutions. So we take the determinant A minus lambda identity. This would be take all the diagonals, or maybe let me just write directly. I forgot this is exactly the determinant. So let's find the determinant. I will, so don't forget, every time we take the determinants, if we want to, using the covectors, don't forget that we need to multiply the signs for every array like this, plus, negative, plus, okay? And you need to also compute the array. If you want to find the inverse, like in your quiz, you need to also multiply with the signs. Okay, I think a few students forget to multiply the signs, and they try to check, and then they multiply again with the matrix, the original matrix, and then it doesn't result with identity. Okay, but that's because you miss out the signs. Okay. Okay, so we can take the determinant. I will take the third row because it's 0. So I will try to write, so negative, so -4, negative lambda, 1, 1, -1. Okay. And then plus -3, negative lambda. This will be -4, negative lambda. Okay. Okay, can I move out this? I will multiply this. Or let me just write this. Four plus, let me check, 4 plus lambda minus 1, so 3 plus lambda, so negative 3, negative lambda. Can I write this as, this is minus, this is plus, right? Same, right? And then I will write this negative 1, negative. Is that correct? Which one? The first one? Eh. Oh, okay. Let me check. Negative. Oh, 5. Okay, so it should be negative 20, negative 5, right? Negative 5 lambda. And then, what? Plus lambda 4, right? Plus 4. Is this correct? And then plus lambda squared. Is that correct now? Correct, right? Okay. Okay. So lambda squared. Okay. So negative 1, negative. Why I feel so slow. It doesn't feel like me. I think I make another mistake. Which one? I know it's supposed to be not 21. why I did wrong? 20. Why I make 22? Why I get 22? It's supposed to be 21, right? Okay. Oh, right. Why I write 22? This feels like, we get nothing here. Okay, now it's, I think it's correct now. So we can make this. Right. Okay. Yeah, finally. So this will be our characteristic equations, then we get 3 lambdas, 3 eigenvalues as we expect. So we have negative. Don't forget I have a negative signs outside that you need to multiply. So lambda 2 will be -4 and -4. Lambda 3 is 5, right? Well, I think the negative sign doesn't matter because anyway you have opposite signs, right? Okay. Just ignore my comments. So we have this, and this. So we could try one by one. Let me write maybe here. So lambda 1 equal -3. So this will be a plus 3, right? And I will put this into the row operations directly. So -4 plus 3 is -1, 1, 1, and then this 1, 0. 5 plus 3 is 8. 1 -3 plus 3 is 0. So I think now it's quite simple to take the row operations. And I think we can directly see that we can make the row 3 as 0, 0, 0, and we have the infinite solutions, right? And then we can just stop there and make sure that all are in a triangular matrix, either upper or lower we could find. So let's take the row operations here. I think we can start with row 1. I will make that 0, this part. Row 3 minus row 1. Okay. This will be 1, 0, -1. This is still 0. And perhaps we can try the R3, 8 R3 multiply with, or maybe just, yeah, multiply with the 8 and then minus the R2. And I think this is take longer. Let me change another one. Maybe R2 minus 8 R3. I think this will be better. 1, 0 minus 1, 0. I will exchange the structure. So exchange the structure. So I will exchange the row 2 and row 3. So this will be 0, 1, 0, 1, 0. And you can see that since R1 and R3 are the same, we could subtract both of them, and we could define maybe the row 3 as 0, 0, 0. So we could just write here. And we get the solutions. We could get the K1 is equal to K3 and K2 is 0. So let K3 equal 1. So we can have the eigenvector for K1 is 0, 1, 0, 1, 0, 1. Okay, we are going to have a break and we are going to continue. Okay, so I think to make our timing class effective, because the second and the third eigenvalue will be very similar method, so you will have to find the eigenvectors, which are going to have the row operations, and simply you need to be careful for that one. So I will just write the result here. So when you have the eigenvalue is -4, this will be equal to the K2 will be 10, -1, 1, or you get the X2 10, -1, 1, e power of -4t. Okay, that's the X2. And then the same thing for this third lambda. So we have 5. Then we have the K3 will be 1, 8, 1. So X3, the matrix will be 1, 8, 1, E with power of 5t. So general solution, let me write on the left part. So general solutions based on x1, x2, and x3, we can write x is C1, 101 plus C2 plus C3 the power of 5t. Okay. I think as long as you then have a problem finding the determinant to find the eigenvalues and then do some row operations, or yeah, I think the best way to approach the 3x3, I believe, is row operations. For 2x2, maybe you could still solve the system of equations by maybe taking substitutions or eliminations, because 2x2 I think is still simple. But for 3x3, to simplify your process, to shorten your process, I think you could go directly writing the augmented matrix, do row operations. Okay, now this is for the distinct eigenvalues. Okay, distinct eigenvalues. So we have another two. If you remember in engineering math 1, we also have the similar characteristic. Distinct roots, and then this is distinct eigenvalues. And then the second one is repeated roots, and we are going to have repeated eigenvalues. The third one, we have the complex. If you remember the complex, that we have the alpha, beta, we also have later, but I think we don't have time for today, maybe next week, or maybe just introductions now. So let's start with the repeated eigenvalues. So suppose that we have the examples like this. We have the characteristics from here. which if we want to find the eigenvalues, then we're going to find these determinants here. So we can write it's plus, sorry. 36 minus 27 is plus 9. So we have repeated value, which we see that the eigenvalue 1 equal eigenvalue 2 equals -3. And of course, for this value only, so let me write for lambda equal -3, we might find a solution for eigenvectors. So let me write the eigenvectors directly. Okay. So eigenvectors, we would find that this will be 3, 1, so that we can find at least one solution for the x1, which is 3, 1, e -3t. So this is one solution, but we want to find the general system or the general solutions. So we need to find the second solution. So let me write here. So we need to find the second solution, which is the x2. Okay, now we have some set of examples that we can illustrate. So first will be this. So for n by n matrices, square matrix, it may be possible, or let me write what is m and what is the multiplicity. So let me write here that, so in, or maybe let me write if m is positive integer and lambda minus lambda 1 with power of m is a factor of characteristic equations, while this, the m plus 1 with power of m plus 1 is not a factor. Then lambda 1 is the eigenvalue of multiplicity m. Okay. So for some n by n matrices, we can find the multiplicity m. linearly independent eigenvectors k1, k2, km, okay, until how many we are having. So like for example, for 2 by 2, we are going to find multiplicity of 2, 3 by 3, multiplicity of 3, that's the possibility. But for more than 2, perhaps we are going to find at least 2 or 3 for the multiplicity. So there are some ideas, okay, that the M can be as much as the row in matrix or less than that. Okay. So in this case, if the M linearly independent eigenvectors is corresponding to the lambda 1, then the general solutions will be C1 K1 E lambda 1 T, and then you will see that it is the same lambda but different eigenvectors. So we can have like multiple eigenvectors with the same eigenvalue, which we can apply in the system. Okay? That can be possibility. But there are other cases which the eigenvectors is only one. Okay, so only one. So only one. Then how we write the system is based on this form. Okay, so we have x1, we call k11 for the eigenvectors, e lambda 1 t, and then for x2, we can have possibility that it might comes k21 t e lambda 1 t. So it's if you remember what we did in engineering math 1, we are going to multiply with the variable itself to make it linear independent. So that's what we do here. But of course, we can have like many multiplicity. For example, well, of course, I think it's the exam at least maybe the maximum maybe 3 by 3. But for example, if it's more like 5, so we may have for 5. Let's say we can have multiplicity 2 options, or 3, or 4, or all 5. So we can have like this long, like how many repetitions that we have. But if we have only like 2 or 3, then we can stop at some point, and then the other 2 will be the original, like the usual solutions, like the distinct eigenvalues. This is only happens with the repeated eigenvalues. I think it feels like intimidating, right? So I think better to write in an example, okay, so that you can see how we could write, and we could see how it came. I have prepared here just in case. Okay, let me check. Oh, this is another case here. This is for the second solution. Let me start with the left one first. So repeated eigenvalues. So let's say we have to solving this 3 by 3 cases for differential equations. So let's directly write the determinant to get the eigenvalues. And I think I should have one more. Oh, I forgot. So before that, this is supposed to be the next part. So let me add another. So let me write again. I forgot to put one example. The question is quite simple, just solving the so let's take the determinant, finding the eigenvalues. And I think I will skip some process just to give you some focus on what is the repeated values and how it applies. So this is 1 minus lambda. Okay, so it's equal 0. And then suppose that after we find the determinants, we get that this will be equal to negative. And we see that we have the multiplicity. Multiplicity for lambda plus 1. This is, we have 2, m is equal to, so lambda 1 is equal, lambda 2 is equal negative 1, and lambda 3 will be 5. Okay, and then as usual, we find the eigenvectors for all of eigenvalues. So for lambda equal negative 1, we take the row operations, take it 0. So 1 minus minus 1, so it's 2. And I think quite easy to solve, right? So you can just subtract, and you will get some rows that has 0, 0, 0, which you are going to get both rows. You can exchange the rows, and you can make this in the top. This will be 0, 0, 0. Now we have k1 plus or minus k2 plus k3. This is equal 0. Or we can write k1 in terms of k2 and k3. So we can have some combinations here. So either we can have k2 equal 1, k3 equal 0, and k1 equal 1 and k2 equal 1. Okay, or we can have, for example, if we let k1 1 or 0, k1 0, k2 1, k3 1. Okay. So we let the k2 and k3 as our choices. So we choose the k2 and k3. So either 1 0 or 0 1, and then it will give the k1. Okay, just to make sure that we are going to have a proper combinations. And then based on that, we have k1, which is 1 1 0, and k2 is 0 1 1. Well, you could write like maybe your k1 is 0 1 1 or your k2 is 1 1 0. That's okay, no problem. And since these two eigenvectors, so since both eigenvectors are not constant multiple of another, then we can write the solutions directly from this k1 and k2 using the same eigenvalue. So x1 we can write as 1, 1, 0 multiply with e negative t, and x2 will be 0, 1, 1 e negative t. And of course, don't forget the last eigenvalue. We need to check for eigenvalue equal 5. So eigenvalue equal 5. This will be negative 4. This is negative 4. Oh, sorry. And take another row operations. And after some row operations, we get and it implies k1 minus k3 equals 0, or k1 is equal k3, k2 plus k3 is equal 0, so k2 is minus k3. So let k3 equal 1, and we get the k1 and k2, and we can write k3 will be 1, negative 1, 1. So x3 is 1, negative 1, 1 e 5t. And this is, I think, one of the unique equations in matrix. So if you write the whole solutions, so general solution, okay, so that's the general solutions. And this is what we call the symmetric. This is what we call the symmetric matrix. Okay, symmetric one, 1, 0, 0, 1, 1, and 1, negative 1, 1. So symmetric means that A transpose is equal to A. So if you can find that the system, so let me write here. So if you can prove and find if the equations is symmetric, and of course it has the entries, then we can find and linearly independent vectors. Let me just write K. Okay. So you can always find K, K1, K2, K3, as long as you can find that the differential equation is symmetric. Okay. But this is like a special kind of matrix that's unique. Okay. So I think if your calculators can input in the matrix form, it will be very helpful for you. Okay. Because you can check, and if it has some functions related to matrix, it's also can really helpful. So you can transpose, you can take inverse, maybe input the determinants, and you can confirm your results. Okay, you can confirm your results. Okay, just to help out to make sure that your answer is correct. Because I know, like, when you write like really long equations, you tend to make mistake in the middle. So in order to prevent that happen, you can check first maybe what is going to be expected as the answer, and then maybe if you have like a problem in the middle, maybe you can quickly trace your solutions and then find out which one is the mistake. Okay. Now another thing, okay, before we move to another example for the repeated eigenvalues, similarly with the engineering math 1, we have the how to find the second solutions. So let me explain first. Go for here. So let this as this is another eigenvalue, and this will be the second solutions. Okay, suppose that, oh wait, this is wrong. This is supposed to be this one for the 3 by 3. So the second solution, let me just write again here. I forgot to write this one. So this will be second solutions. Suppose that second solution can be written in the form of the K T E lambda 1 T. Similar what we have before, but let me introduce some coefficient, another coefficient P, and we define the K as eigenvectors, and P as another coefficient. Okay. Our system is x prime ax. Okay. So we are going to substitute this into the system. So we are going to have a k minus lambda 1 k t e lambda 1 t plus ap minus lambda 1 p minus k. Just basically just substitute the x2 inside, and then e lambda 1 t equals 0. Okay. So we must have, or we need to solve the a minus lambda 1 k equals 0 and a minus lambda 1. Oh, I forgot the identity. P equal k. Okay. So simply, this is going to be the eigenvector. And by solving this one, we get, so our expectations by the first equation here, we find one solution, right? One solution, which is the previous example, we take that, oh, we can find at least one solution, right? For a typical eigenvector. And then to find the second solution, solve to find second solution, x2 or maybe not solve p to find second solution x2. Okay, let me give you some illustrations. The previous examples, we are given that the x prime is equal 3, 2, negative 18, negative 9, right? And then we get, after we get the eigenvalues, we get that the k1 is 3, 1, x1 is 3, 1, e. Okay, so this is the first step, finding eigenvector. We find the x1, and then to take the second solutions, so let me write again. So identify, or we know that k, let's say 3, 1, and then p, we can just write p1, p2. Okay, so it's like an additional factors, and then we are going to solve this p. Okay, we need to find the p. So what we need to do is we are going to use the, so this is eigenvalues. I forgot the eigenvalues is negative 3, right? So we are going to use the row operations, or because it's 2 by 2 matrix, I don't think we need row, but if 3 by 3, we need row operation. So we are going to solve a plus 3 identity, multiply with p, need to be equal to k. So we are going to take the plus the 3, so 3 plus 3 is 6. So this is going to be a plus 3, so it's 6 multiplied by p. P for the variable 1 is p1, so let's just write this as 6p1. And then negative 18 p2. This is k1, so k1 is 3. Okay, so this is k1, k2. Okay, and then the second equations, we can write 2p1 minus 9 plus 3, it's a minus 6 or minus 6 P2. So we can solve this. I think we can solve just taking P1 and P2 we get. We can choose P1 half so that P2 is 0. There will be some other solution as well. Like for example, you can also have, if we choose P1 equal 1, then P2 will be 1 over 6. But if you choose P1 equal 1 over 2, then P2 will be 0, and then the P so thus P is half 0. This is to make it simplified. Then we can offer the second solution as 3, 1. But again, the vectors P, it could be many variations. So the general solutions could be X, okay. The X1 we can just write as it is. But for the next terms, you need to be careful here. Let me write carefully. I think I make it too big here. Okay. So general solutions will be plus C2 and this is 3, 1 T E negative 3 T plus another one. So we have this it seems that it's like a conjugated solutions. So this is the X1, this is the X2. So what's happened if, so this is only for the 2 by 2. So if we have 3 by 3, then we need to add another factors. So this is, the additional factors is P. Then if we need, or if we need to solve the 3 by 3, then we add another factors Q. But basically, the algorithm will be very similar. So we are going to have this solutions here. We need to solve this, find the P, and that P will be our possible solutions or possible factors to be multiplied with our repeated eigenvalues equation. So this is for the repeated eigenvalues. So again, first you need to decide how many multiplicity you have, and then how many distinct values for the eigenvalues. So maybe you calculate the eigenvalues that is distinct first. You keep this in this way, and for the repeated values, then you can do this way. You can, maybe you have second solution, third solution, like it can be increased. There will be another example for 3 by 3, but I think maybe I'm just going for basically this one here. This is 3 by 3. So let me erase this for a while. This is for the 3 by 3. So this is for 3 by 3, multiplicity of 3. So this will be solving. So now we have x3 for the multiplicity of 3. So we solved. So we need to solve k, p, q. So first is finding the one solutions, and then find the second with this, and then find the third. I think I need more time for the example here, so I think I will just finish up until here. Okay. So I think we can have. I think next Monday we are going to revisit again the repeated eigenvalues. And before we go for complex eigenvalues, which a little bit more complicated because it will have like an alpha, beta. If you remember, you have the complex in a set of real numbers. So how to define it? Well, anyway, that's similar to what you have in the engineering math one. So before we going to that complex eigenvalues, before you forget everything in this part, this thing, and repeat it, let me go for exercise, okay? Before the complex eigenvalues, so that you can have like familiarity in the process, okay? Okay, so the idea is we find eigenvalues, we find the eigenvectors. Okay, so that's basically that is the importance one, and the unique case if they are multiplicity or repeated eigenvalues. So that's when we need to take the second solution or the third solution. So depends on how many rows, column we have in the coefficient matrix. Okay. And I think if you already try to understand what it is, like in the sense of algorithm on all the differentials, you will see that with this method we can put a whole differential equations in a set of, like, maybe if we need to models like many points or trajectories, either in maybe in physics or in electrical, like in the currents. You can have like later on maybe in mechanical also some vibrational equation, like related to vibrations. You need this differential equations, and the eigenvalues method will really helpful because it will simplify the models, and you can just take the parameters based on the eigenvalues and eigenvectors. Okay, and then that's how I think the more you are going into the maybe year by year, you will see that you will appreciate more what we have in the foundations of the differential equations. Okay. So I think I will end up until there. So and the quiz, if you haven't got, or if you want to give to your friend, you can take it. I'm afraid if I keep too long, I will lose it. Okay. Okay, any questions so far? I think we are going to have an exercise more for this one to help you out and familiarize yourself with the solving the differential equations with matrix or eigenvalues, to be precise. So if there's no questions, let me give you the QR code.